Okay, so we talked about sunny San Jose yesterday and how the population was increasing by 1.36% roughly over this 10-year period. And we said extrapolating out to 2018 when T is 28 was a little bit unreasonable. The model over-predicted the population. So remember that models are only good in predicting or projecting possible values. They're not absolute. And again, if you extrapolate outside the data, if this data was collected from 1990 to 2000, the further you go past 2000, the more likely you're going to be off, right? Because as we said yesterday so eloquently, stuff happens, right? And simple mathematical models don't take that, and modicals take that into account. All right, so here's another city that is not like sunny San Jose. This one is Detroit, Michigan, and you might have heard about Detroit in the news. This one has taken data from 1980, so over a 10-year period from 1980 to 1990. I looked at 10-year spans, okay? So T equals 0 corresponds to 1980. So we're going a little bit further back, 10 years further back. Oops. According to this model, what was the population, bless you, of Detroit in 1980? Yeah, 368 citizens, right, or people. So it was a bustling town in 1980, 1.2 million people, pretty large, right, pretty large. What has happened to Detroit since 1980 according to the model? Yeah, these citizens are decaying. It's becoming like Walking Dead type stuff, right? That's not what we mean. The population is decaying. People have been leaving. Now notice this model was predicted prior to the automobile disaster that happened in the early 2000s where the auto industry folded and the federal government had to come in and rescue it and people left Michigan. So this was already happening before that. So let's go ahead then and identify the decay factor and the decay rate. So I might ask you these types of questions on the quiz tomorrow also as well, additionally too. Which one of those is easier to find from the equation, the factor or the rate? The factor, because the factor is just the base. Yeah, 0.9858. Good. That is the decay factor. Is the decay rate just that number as a percentage? No. Okay? No. That is wrong. It is always the difference of that number as a percentage from what number? 100. Yeah. So because that's less than 100, we go ahead and write 100 above, and we subtract, and we do our borrowing all the way through. There's a 10, there's a 9, there's a 9, there's a 9. And we subtract, we get 2, 4, 1. So 1.42%. So what we're saying then is over that 10-year period, the population of Detroit was decaying, or decreasing might be a better word, by 1.42%. So people were leaving Detroit at a faster rate than people were coming in to sunny San Jose. So is it safe to assume that not all the people that left Detroit went to San Jose? Yeah, maybe. Yeah, that's probably safe to say, regardless of the numbers, right? All right, so can you do that tomorrow on a quiz? Heck yeah, you could. All right, so let's go ahead and do something here, just kind of for fun. Let's go ahead and see what the population would be in 2018. Would this be a reasonable thing to do for this model? No, because 2018 corresponds to what value? If 80 is T equals 0, 38. Yeah, 38 years later. That's a long ways outside of 1980 when we started, and it's 28 years outside of 1990. A lot of stuff can happen between now and then, like, I don't know, the automobile industry collapsing, right? Okay, so let's go ahead and say the population at 38 is, and if you have your calculator, feel free to type it in. You can just type it into the home screen because we're only going to do one calculation. I'll do it with y'all. Oops, clear all that. Get to the home screen, clear, flush. Okay, here we go. So 1,203,368 times 0.9858 caret to the 38th power. Does that look right? Okay, here we go. Big bucks, no whammies. Oof, this predicts that the population is 69883. We'll call it 3. We'll say that last person hasn't quite left yet. Huh? Yeah. People. Notice the decline. Wow. If this model is correct, almost half, right? Not quite. 100,000 short of a half. Yes. Well, no, I would probably say to the nearest whole person. Yeah, to the nearest whole person. Yeah. Do you think the actual population of Detroit today is greater than that or less than that? Greater? You think that the model, again, overshot? Detroit has been on the rise here in the last few years, but there are still several places in Detroit that are ghost towns. You can still get cheap real estate in Detroit. Here's the actual population of Detroit last year. 673,104. Yes. So believe it or not, the population of the model did not. It undershot. Okay. When we did San Jose, it overshot. This one undershot. There's actually fewer people there than the model predicted. And of course, maybe what's the reason for that? What big event happened outside the data? Automobile industry crashed, right? What? The industry folded. What did I say? I missed it. Oh, murders. Oh, it's pretty high crime. Yeah, absolutely. Pretty high crime as well. So these take into account mortality rates and birth rates and people just leaving the city, okay? These are census numbers. So anyway, yeah. So Detroit still nowhere near where it was in 1980 when it was a bustling 1.2 million people town. But it's coming back, right? Blake Griffin had like 50 points last week for the Pistons. So, yeah. Okay. Any comments or questions on this? All right, cool. Let's go ahead and shift gears here and talk about something other than people, like bacteria. Oh, yeah. Again, something I know a little something about. I have had 9 knee surgeries on my right knee. Yeah. 2 of them were to replace torn ACL, and the other one was for a torn meniscus. So the other 7 were because I unfortunately got, in both times, post-op infections, really bad post-op infections. And it was because, do I have a picture? I do, but you don't want to see them. It's because bacteria somehow, here's what I would tell you. If you ever have surgery, guys, it's worth the extra $5 to get a sterile room. Okay, I was going cheap, and so I got an infection. All right, and it's because the bacteria reproduce exponentially. Okay, I was sitting at home missing a football game years and years ago, and I was fine. My family went to the game. It happened to be a televised game, so I was watching it on TV, and I felt good in the first quarter. Second quarter, my knee started going, halftime, I was like, oh boy, should I call? Something's not right. And by the third quarter, my knee had swollen so big that to relieve pressure, I actually had to squeeze my knee and milk out some of the bacterial pus that came out through the almost healed surgical scars. Yeah, just to relieve the pressure because it was unbearable. That is the power of exponential growth, okay? I called my family that came, took me to the hospital, another emergency surgery to clean it out. Anyway, bacteria, not all of it is good. Some of it's good, right? You have bacteria in your digestive system that helps you break down food, but not all of it is good. MRSA, MRSE, bad stuff. MRSA, yeah. Okay, so here we go. A small culture of 10 bacteria is placed not into a knee, but into a petri dish. Oh, that's much better, okay? Suppose that the culture of bacteria doubles every single hour. After how many hours will the number of bacteria reach 500,000? Okay, to go from, bless you, 10 to 500,000. Okay, 10 might be like me in the first quarter, like, hey, I'm feeling okay. 500,000 might be like, time to squeeze, right? I had paper towels nearby. I don't know if I'm, yeah, I guess I am. I forgot I was recording. Okay. Here's what we're going to start with. Y equals A times B to the T. Or if you prefer, we could start with A, the amount of bacteria, is equal to A sub O times B to the T. It doesn't really matter. They're both the exact same equation. You're just using different letters to represent the same quantities, okay? But I would recommend using T instead of X because we have time, right? First quarter, second quarter, halftime, squeeze quarter. All right. So we need two ordered pairs. A, remember, is the initial condition. Do we know that value? We start with 10. Yeah, so actually you know A right away is 10. So you can go, I'm going to use the top model. So we're going to say Y equals 10 times B to the Tth power. You can plug that in right away. But I do need another ordered pair in order to find the second value that I'm looking for, B. Do we have another ordered pair? Well, 500,000 is a Y value only. I would not know the T or the B value, so that's not going to be helpful yet. We are given the rule by which it reproduces. So we can actually make ordered pairs if we need them. 0, 10, right? We know that. And if it doubles, so from 10 it goes to 20 every single hour, that would be 1 hour later. 240, so on and so forth. We only need to make one extra ordered pair. Now we can plug that in right here. So at the point 120, we get 20 equals 10 times B to the first. Now that's a lot easier looking equation than the one we just solved in the warm-up. You just divide through by 10 and you get B equals 2. All right, so now you just plug that in. So Y equals the initial value 10 times 2 to the Tth power. Hey, the base is 2. It doubles every hour. Could we have maybe figured that out before we started? Yeah. Remember, if something increases by a constant factor, it's also going to be exponential. And as we already said, that factor is the base. Very good. The base. So in the future, if you were given this situation, you wouldn't have to waste, those 40 seconds or whatever it took to do this. You could go straight to here if you wanted to. But the whole purpose of a model is to use it, not just to come up with it and walk away. So now that we have that, we can either use it in one of two ways. We can plug in a value of T in hours and extrapolate what the population is going to be, or we can set it equal to a desired population, like maybe 500,000 is the critical, and we want to know how long does this person have before it gets to that point, right? That's what we have, the squeeze point. So that's what we have here. So we're going to set 500,000, yeah, equal to our equation, 10 times 2 to the Tth power. Now, when we start studying logs in here, there's going to be a way to solve this algebraically using logs, but we haven't gotten there yet. So we're going to solve this on the calculator Medora. So what you're going to do is put this into Y1 and put this into Y2, and then just look to see where they do what? Intersect. So I'll do that with you. If you have a calculator, maybe they didn't clear it out. All right, so here it is in Y1. Hey, it's Coach 5 for everyone.
Hello.
Yeah. Or today, he's not 5-4, he's 2-4. Yeah. Coach Dos 4. Yeah, Dos 4. 2-4. No, whatever. He's basketball, girls basketball, and high jump. All right, so 10 times 2 to the x, there is, of course, we use x instead of t. That's in Y1. And then in Y2, we put 5 with a bunch of zeros, okay? Now, if you hit zoom 6, you're going to be like, I don't see. And I'm like, good. You shouldn't. Okay? So let's go to a reasonable window. We're trying to see where it intersects at 500,000. You're only going up to 10. So let's go to something like, 600,000. Give it a little bit more room, or maybe even 1 million if you want. The only thing that should be something that you're playing with is the X max. How many hours do you want to go by? 16 hours? Okay. You do it. I'm going to give it a day. I'm going to go 24. That seems reasonable. You might have to come back and adjust that number. Hit graph. Got it. Good. If I didn't see it intersect, if I saw it was still intersecting off the screen, I would set my X max to something a little bigger. All right? Now, you don't want to scroll over there with the trace button because your calculator can actually compute it to 3 decimals. So we hit second trace, right? Second trace is your calculate menu, and which option do we want? Intersect number 5. Now, here's the cool part. If you only have 2 curves graphed, and they only intersect once on your screen, all you have to do is find the enter button and say enter, enter, enter. That's it. It'll automatically go first curve, second curve, and find it. Enter, enter, enter. And notice it has the X or T value down there. So underneath there, to 3 decimals, we're going to put T equals 15.609 if you truncate, which I'm a big fan of, or if you just have to round because that's how you were raised, 610. You would need that trailing 0. Okay? Don't put both, put one or the other. And then you put units at the end. Okay? Now notice that is pretty rapidly happening. That is less than 1 day. It takes less than 16 hours for that bacteria to go from just a population of 10 to 500,000. What's going to happen in the very next hour? Now you're up to 1 million. Woof. Okay, so this person needs to get help fast. Okay, and luckily Dr. Templin was on call. All right. Anyway, any comments or questions on that? Let's do one other thing here, because I could ask you to use it in another way. Determine, using the same model, how many bacteria after 24 hours. Ooh, okay. Spicy. Like if someone waited, would there be hope? Could they still fight it off, or would they be dead? All right? It could happen. Very serious. The power of exponential growth can kill a patient very rapidly. Okay, so here's the etiquette on any kind of quiz or test. If I give you the Y value, you have to show me that you're setting the equation equal to the Y value, and then underneath there you put T equals with units. If I give you the input, it's a little bit different. You have to show Y of the input, or if you're calling it A, whatever the name of the function is, A of the input. But you show it like that. Now, if you do it on the graph screen, remember, it will work. But your window, your X max, X min, have to contain that X value. We only went from 0 to 24. So if I'd ask you for Y of 50, you couldn't do it on the graph without resetting your X max window. That's kind of bothersome. So the way I'd prefer you to do this is from the home screen. So if you get out of there, go to the home screen, alpha trace, not second trace, but alpha trace, gets you to your shortcuts. We have our equation for the exponential in Y1. Open it, type in a 24, just like you would have on your paper/iPad, and hit enter. And whoa, holy Jehoshaphat. That's extra spicy right there. I don't even know how big that, I have to count from the right 3 spaces just to figure out how big that number is. That's like a gazillion, right? 167 million bacteria. In 1 day, it went from 10 to 167 million. That's faster than rabbits, folks. Okay? We're going to need a bigger Petri dish. Yeah. All right. So there's the etiquette. I give you the output, you set it equal, graph, find the point of intersection. I give you the input, you do that. That's after we found the model ourselves. Okay. Comments or questions on that? All right, let's go to example 6. What if the initial bacteria culture from example 5, y'all remember example 5? Yeah? Okay. What if that population of 10, instead of doubling every hour, tripled every 2 hours? Would that be faster or slower? It'd be a smidgen slower, right? Because if it triples every 2 hours, that's less quick than doubling every hour, because that would be quadrupling every 2 hours, right? So this is a little bit slower. So this type of bacteria, the patient would have a little bit longer, right? I want you to determine what the new equation would be, and then how long would it take for that bacterial culture to reach 500 grand. So I'll give you a couple of minutes to do that. What would the new equation be? and how long would it take? If you don't have a calculator, you can at least set up the equation for how long it'll take, and then we'll do it together. Gesundheit. If you're cooking, keep going. Bless you. If you're stuck, could we just say then that it's because it's tripling every 2 hours? Could we just say that the model is y equals 10 times 3 to the tth power? No, because that would be tripling every hour. We want it to triple every 2 hours. Okay? So you might know exactly what to do to that to make it work. But if not, let's see what we can do otherwise. We can create our own ordered pairs again, t comma y or t comma a, whatever you're using. So we know it's still 0, 10, but now it's tripling, so 10 goes to 30 in 2 hours. So there's your second ordered pair. Now because we know the initial condition, we know that we could start with y equals 10 times b to the tth power. We can just plug in the 10 for a automatically. And then we can use the second point at 2 comma 30. You get 30 equals 10b squared. Now, when you solve, you get b squared equals 3. Is 3 a perfect square? Nope. So what we do remember is we raise both sides to the reciprocal power, and we leave it as 3 to the 1/2 instead of the square root of 3. We don't want radical bases. We'd rather absorb them into the exponent. And we don't need to consider the negative one because we can't have a negative base. So then you plug that back in here, and you get so y equals 10 times b, which is 3. And remember, all you have to do is multiply. So it's 1/2 times t, or you can actually write it a little bit nicer, 3 to the t divided by 2. 1/2 of t is the same as t divided by 2. Okay, so that is going to do it for us. Now, looking back in hindsight, what does dividing by 2, why does that work? We want it to triple every 2 hours. So if we divide by 2, now every multiple of 2 is going to give us one extra value of t, right? When t equals 2, it becomes 1. When t equals 4, we get 2. When t equals 6, we get 3. There you go. So you wouldn't have to, again, do it this way. If you want, moving forward in the future, you could say that's, of course, your initial value. This would be your growth or decay factor, either one. And then this up here could be t divided by the time for the factor to occur. Okay, so we've got it. Let's look at the follow-up. Oh, we need to answer the question now. We want to know how long that would take to equal 500,000. So now, if you want to put the equation first and set it equal to 500,000 on the right-hand side, that's really the same thing. And now all you have to do is go back to the calculator and change just a couple of things in Y1. I'll leave that there for y'all to see. We'll go back to it. All right, so all I got to do is change the base from a 2 to a 3 and come up here to the exponent. Oops. Go up to the exponent, please. There we go. And I'll divide it by 2. and I still have 500 grand. Let's go ahead and get graphed. The same window might work. Okay, but notice it's closer to the right end of the graph. Second trace number 5, and then enter, enter, enter. You can almost click your heels 3 times when you do that. Enter, enter, enter. And it just magically appears. So underneath there, we'll put T equals 19.697, and then the units are hours. So this person bought themselves about 5 extra hours from the other model. Or no, sorry, 3 or 4 hours. Still, within 1 day, it's going from 10 to 500,000. Okay, so here's what I want you to do. What if the model, where T is measured in hours, still in hours, what would the model be if the population of 10 that we started with still tripled, still starting with 10, but it tripled every 7 hours, every single day, and every 20 minutes? See if you could figure that out on your own. What would the new model be if it tripled every 7 hours, every day, and every 20 minutes? What would be the same, first of all? Would the 10 still be the same? Yes. Would the scale factor of 3 still be the same? Yeah, it's still tripling. So the only adjustment we're going to have to make is in the exponent. Okay, and go ahead and see if you could do that for all of them. T divided by something, T divided by something, T divided by something. You can leave your calculators on the desk if they're not yours. If they're yours, you can take it with you. All right, we're kind of running out of time. We got a minute and a half. If we're measuring T in hours and it tripled every 7 hours, then part A would be T divided by 7. Good. If it tripled every day, would we divide it by 1 per day? No. We have to know there's 24 hours in the day. Good. Now, if it tripled every 20 minutes, that's going to be more rapidly. Would we divide this by 20? Yeah, we need to convert 20 minutes to hours. 20 minutes is 20/60th of an hour. Okay? 20 minutes is 20/60th of an hour, which is a third of an hour. So if we divide it by a third, that's the same as stay, change, flip, multiplying it by what? 3. Cool. So now it's not in the denominator. What would that 3 do to the graph? Would it compress it or stretch it horizontally? It would compress it horizontally, which would make the graph steeper and grow faster. Look out, dude. You need to get there at the end of the first quarter. All right. Quiz tomorrow. Enjoy the rest of your vinegar day.